Hello and welcome to today's lecture. In the last few lectures we talked about basics of antennas. We talked about simple dipole, monopole, slot and loop antennas, and also we just looked at the basic introduction of microstrip antenna. So today we will continue from microstrip antenna. So as we had seen, a microstrip antenna is a very simple configuration. We have a ground plane on one side and we have a metallic patch on the other side, and here is a feed point. So we have just given you one example over here where we had designed the antenna at about 1.8 gigahertz. So this is how the VSWR varies, and we define bandwidth for VSWR less than 2. So over here if we see 1.76 is roughly this frequency, and it is about 1.855 that goes there. So the total bandwidth is about 95 megahertz, and we define percentage bandwidth as bandwidth divided by the center frequency, which is coming out to be 5%. So here in this example it shows the radiation pattern of a microstrip antenna. So for the designed antenna we have shown the radiation pattern at 1.8 gigahertz, which was the center frequency. So you can actually see here there is a one yellow curve here and then there is a one red curve here. So it actually shows E plane and H plane radiation pattern, and you can also see that there is a back radiation here. So we define front to back ratio F by B. So from maxima to this value here, each scale here is a 5 dB, 5 dB, 5 dB, so that is about 15 dB. So front to back ratio is about 15 dB. Now this is an example of a microstrip antenna array. So one can actually see that this is a 16 by 16. So there are total 256 elements are there with a feed network. So you can see that all these elements are being fed by a microstrip line, okay, and this whole antenna was designed at 35 gigahertz, and you can see that all these number of elements are fitted in a very small size of just 10 centimeter by 10 centimeter, which is like 4 inch by 4 inch. So as we move along the course, we will talk in detail about how to design all these antennas and arrays. Now that feed network creates a lot of problem because of large feed losses. So here we have actually designed an antenna where this is the fed microstrip antenna, and that microstrip antenna is radiating, and that radiation from this microstrip antenna excites the patches on the top. So this is also known as space fed microstrip antenna array. So you can see that this is the top view of this here. So that is a 4 by 4 array, and we are actually feeding just a single element which is exciting this one. So here there are no feed losses. Then let us just look at helical antenna. Helical antennas are nothing but you take a wire and just bend it around, and how you bend it is important. You can bend it on a simple dielectric rod which can be hollow or a solid, or you can provide some support structure also. There are 3 different modes in which an helical antenna can operate: a normal mode, axial mode and conical mode. In fact, the same helical antenna can work in either of the mode depending upon the frequency of operation. So for normal mode, circumference is which is equal to pi d. So this is the diameter. So pi multiplied by d is circumference. If that is much less than lambda, then that will actually radiate in the normal to this particular axis. So this is the helical axis, it will radiate in the normal direction. That is why it is normal mode. In fact, this is very similar to, you can say, a dipole antenna or a monopole antenna, which is like this here. So the radiation is maximum in this. So instead of having a large monopole antenna, now that large monopole antenna is made compact, the height is reduced. So in fact, I did mention to you, for let us say a mobile phone at 900 megahertz, we would have a wavelength of 33 centimeter. So we need maybe about roughly 9 centimeter height, but here the height can be as low as just 2 centimeter. The other mode is known as a axial mode. In fact, what it really implies is axial mode, the maximum radiation is along this particular axis. Here you can see normal mode, the radiation is maximum in this direction, which is perpendicular to the helix axis. So here the condition is that circumference is equal to pi d, which is equal to lambda. Then there is a conical mode also, where circumference becomes n times lambda, where n is 2, 3 or more. However, I just want to tell you this mode is very rarely used. So in our coverage of helical antenna, we will focus on these two modes. Then the next one which we will cover is a horn antenna. Now there are two main types of horn antennas. One is a pyramidal horn antenna. In fact, there are variations are there also. So for example, if this is a rectangular waveguide, so if we just flare in one plane only, then it can be E sectoral horn antenna or H sectoral horn antenna. But if it is flared in both the direction, that means you can see that this width is expanded and this length is also expanded. So this is a pyramidal horn antenna because it just looks like a pyramid. So over here E field is uniform in this direction, vertical, and since this is a metal plate here, so E will be 0 here, which is a corresponds to voltage equal to 0. So E variation along this axis is it goes from 0 goes to maximum value and then it goes to 0 here. So the variation is half of sine or cosine depending upon how you define the angle, and in vertical direction it is E field. Now for this particular case here, in fact we have gone through several books and journals. Now what we realize that they do give lot of information about what will be the E field, what will be the H field, what will be the radiation pattern and so on. But however, we found that majority of the books do not give details of the coaxial feed, how to feed this directly. Many a times they will show that horn antenna is fed by a waveguide and then at the waveguide they use waveguide to coaxial adapter here, but that makes the whole length very long. So we will also mention how to design this pyramidal horn antenna, what is the role of the coaxial feed. In fact, while I was investigating about this over here, I came out with an idea that why use a coaxial feed here. We can use coaxial feed to excite a microstrip antenna, which is shown over here, and we actually used a conical horn antenna. So if you see here, this is a conical horn antenna, and over here we have a microstrip antenna. So one can feed a microstrip antenna. So it is very simple to design a microstrip antenna even for different polarizations also, or it can be used for multi-band operation also, or we can design antenna for whatever thing we want, a horizontal polarization, vertical polarization, circular polarization, dual band, multi-band, and this horn antenna we utilize to amplify the gain of this particular antenna. So we used advantages of both microstrip antenna and horn antenna, and we gave a name microstrip antenna integrated with conical horn antenna. So we will look into the details of this in time to come. Then we will talk about reflector antenna. Now there are three main categories of reflector antennas are there. One is known as a planar reflector. Planar reflector is nothing but you have a, let us say, a dipole antenna, and you put another, let us say, a metallic plate here. So that will be a planar reflector antenna. So what actually it does is that dipole will, let us say, radiate uniformly in all the direction by putting this reflector. So the wave which is incident on this particular plane will reflect and it will go in this direction. So basically omnidirectional will now become directional. So it will radiate only in this side and it will not radiate in the back side. So that is a plane reflector. Instead of this, we can also use a conical reflector. So in conical reflector, what we do, we put, let us say, this antenna on a corner reflector. So we have a one corner and the dipole antenna or any other element is put in between. So by changing the angle, so it can be a 30-degree corner reflector or 60-degree or 90-degree or 120-degree. Plane will be a 180-degree. So plane reflector will be a generalized case of corner reflector antenna. And by changing the corner angle, one can actually change the gain of the antenna. which is kind of obvious. So, if it is like this here 180 degree, it will now radiate in 180 degree. If I make it narrower, so what will happen, because of the reflector now, it will actually radiate only in this particular cone here. So, that is how the conical antenna will give us a little higher gain. So, typically a planar reflector may give us additional gain of about 3 dB, but a corner reflector can give a gain of additional 3 dB to even 7, 8, 9 dB gain also, depending upon the corner. However, the parabolic dish antenna, they are actually used to design very high gain antenna. First of all, let us just look at a very simple thing. So, you might have studied about a parabola equation even in your high school or initial engineering courses. So, what is the definition of a parabola? That rays which are coming parallelly from the far away, after the reflection they will concentrate at the focal point. So, it is the same principle which is used in the case of parabolic dish antenna also. So, let us say if it is in the receive mode, so all the signals which are coming from far away point will reflect from here and they will focus on this. So, at the feed point we put an antenna. It can be done in other way around also. So, feed is there, so we feed the antenna, it will radiate in this direction and then it will reflect and it will go far away point. So, in fact, a majority of the very high gain antennas, so when we talk about a very high gain antennas, let us say 30 dB, 40 dB, 50 dB, 60 dB and beyond, reflector antennas are the only solution right now. In fact, there are antennas which are made even a half a kilometer diameter also to actually have a very narrow beam, which implies also very high gain antenna. So, reflector antennas are used. So, parabolic reflector is just one type of the antenna, but variations are also there in parabolic, like this is known as a prime focus feed reflector antenna. There are Cassegrain reflector antennas are there, and even the shapes are different also. There are spherical reflector antenna, there are cylindrical parabolic reflector antennas and so on. So, the biggest advantage of these reflector antenna is that it has a very high gain which cannot be achieved by any other antenna as such. The only disadvantage is it occupies very large space. Actually speaking, people were using parabolic dish antenna for 25 dB or even 30 dB. We have actually redesigned these reflector antenna and realized a microstrip antenna which is flat, lightweight, occupies less volume and so on. So, when we discuss reflector antenna, we will also tell you what we did. And also for the feed, lot of different types of feeds can be used here. So, earlier ones had used a horn antenna as a feed, or in fact they had used axial mode helical antenna which generates circular polarization over here. So, that is what it is used. We have even used a microstrip antenna here also to reduce the size of this particular feed. So, we will see what are the different things here. So, basically when we want to do the derivation, so what we do, from here we take the path and this path over here. So, the beauty of this particular thing is that actually speaking, all these waves after reflection they are in the same phase. Then after that we will discuss about Yagi Uda antenna. As I mentioned earlier, these are the two Japanese inventor who invented this antenna. What is the concept here? So, what we have here, we have a fed dipole here, and you can see here there is a small gap because there will be a balanced feed over here. So, this will be plus and this will be minus current here, and we have here a reflector antenna. Now, you can see that it is not using a very large reflector antenna, it is slightly larger than this here. So, typically a fed dipole should be approximately equal to lambda by 2, but when we talk about dipole antenna, we will see that this length should be slightly less than lambda by 2, and the reflector antenna is taken slightly larger than fed dipole. So, what is the purpose of reflector antenna? Let us say this dipole antenna will radiate like this. So, that is the magnetic field. So, that will reflect from here, since it has a larger dimension, it will reflect in this direction. Now, these are known as directors. So these directors will actually speaking, the reflected wave goes in this direction and they direct the beam in this particular direction. So there is a maximum radiation is along this direction. So if you think about the array theory, so in arrays, if all the elements are fed in the equal amplitude, they will radiate in the broadside direction, but this is radiating more in this particular direction. This is also known as end fire array. The advantages of using multiple directors are that if there are more number of directors, gain increases. Just think about on the lighter note, think about let us say in IIT, if we have more directors, you really think that the gain will increase? Not really. That is why we do use in IIT, we have a one director and we have two deputy director, okay, in any organization also. So we have generally one director, but you can see these wires perform much better. So more number of wires or directors will improve the gain in a more significant manner. Now here what we have done, we have used the printed version of this Yagi Uda antenna. So instead of using a fed dipole and using two different feed here, we have actually used a printed dipole antenna. So this on one side of the substrate, we have this half wave length, half of the dipole, and on the other side of the substrate we print the other half of the dipole. So the total length is about approximately lambda by 2. So this will be lambda by 4, this is lambda by 4, and this is a coaxial microstrip transition. So from coaxial line we are transmitting and that is actually generating. So that the top line is there, so one line is connected to this one and the bottom line is connected over here, and this reflector is printed and these are number of the directors. So when we talk about Yagi Uda antenna, we will see what happens if we add more number of directors, how much gain increases and what are the different parameters. Then the next topic which we will cover is a log periodic antenna. A log periodic antenna, the difference between log periodic antenna and Yagi Uda antenna, let me first tell. In case of log periodic antenna, we have multiple number of dipole antennas. Each of these dipole antennas are fed. How they are fed? Let us see, this is the feed point. You can see that it is connected over here. Now the feeds, these are connected in the opposite phase. Then this one here comes here and this here goes there. So think about if this is plus, this is minus. So now minus goes there, plus comes here. Then this plus goes up here, this is minus goes here. So each of these elements are experiencing 180 degree phase shift. So here all the dipole antennas are fed, whereas in case of Yagi Uda antenna, only one dipole is fed. All these are not fed at all. In fact, these are also known as parasitic element. What does really parasitic mean? Parasitic means something which depends on other, and also you can see there is a no gap over here, okay. You can simply put a length here, and just to tell you, so this is approximately or slightly less than lambda by 2, it is greater than that, and these directors are all have a slightly lesser dimension than fed dipole. Whereas in case of log periodic antenna, the concept is slightly different. Here all the elements are being fed with 180 degree phase difference. Also the length of these dipole antennas, they vary in the logarithmic manner. Even the spacing between the different elements also vary in the logarithmic manner. Ideally, even the diameter of these dipole antennas should vary in the logarithmic manner. So there is a ratio here. So L2 by L1 is defined as 1 by tau, and that is known as the log periodic ratio. So if you see here, if this is the length L2 here, then this is L1. So we take the ratio. Similarly, all the other lengths, so Ln plus 1 divided by Ln. So if n is let us say 1, which is 2 and 1. If L is let us say 4, so this will be L5 divided by L4. The same thing is also valid, this 1 by tau holds good even for R2 by R1, which is the distance from the apex and this is the angle which all these dipoles are making. So, this is also known as angular variation of these dipole length, and then even the diameter spacings, all these things should vary in the logarithmic manner, but you might see that where is log here, right. So, actually the log comes into picture if we take the log of both the side. So, log 1 will be 0 minus log tau will be equal to log L2 minus log L1. So, we can actually say that all the dimensions are varying by a factor of log tau, okay. And so, every next dimension will be scaled. So, from here to here to here to here, the dimensions will keep on increasing by logarithmic of the function. Same thing should happen for the diameter. However, practically all the diameters are not always changed. So, suppose if there are, let us say 10 elements or 20 elements, so finding the wires of 20 different diameters will be difficult. So, generally they are grouped into 3 or 4 different diameters. Now, the purpose of Yagi, Uda and log periodic, they are actually different also. So, Yagi, Uda antenna in general are designed for higher gain. However, there is a limitation on higher gain also. Typically, a Yagi, Uda antenna can achieve about 7 dB for about 3 to 4 element to about 10 to 12 dB. Very rarely people use for 15 dB or more. But here the limitation is the bandwidth of the Yagi, Uda antenna is relatively less. Of course, lot of research is going on currently where they are trying to increase the bandwidth of Yagi, Uda antenna. However, log periodic antennas, the major emphasis over here is the bandwidth, okay. In fact, the log periodic antennas are available which may have a bandwidth of 1:10, for example 1 gigahertz to 10 gigahertz, or let us say 300 megahertz to 3 gigahertz. So, 1:10 is very easily achievable using log periodic antenna, only thing is the number of elements are large. Also, log periodic antennas can give us a directional beam with a gain which may vary from 7 to about 10 dB or so, but generally people, or in general practically we do not design log periodic antenna for very high gain. So, that is about 8 to 10 dB is generally the limit for log periodic antenna. So, we will also see that how the bandwidth of these things change. So, we will talk about that what is the effect of the diameter of the dipole antenna over all bandwidth, and what is the spacing factor, how to feed these antenna, how to practically realize these log periodic. In fact, there are a lot of printed variations are available today for log periodic antenna. This is also a printed variation. In fact, I just also want to mention Yagi, Uda antenna was very popular at one time for receiving the TV signal. So, let us say in Mumbai we have a TV transmitter at Worli, and that is transmitting in all the directions. So, let us say somebody sitting at IIT Powai, so has to direct antenna towards Worli. So, they had to use Yagi, Uda antenna. In fact, what was the popular thing was, instead of using a normal dipole, they had actually used a folded dipole. The advantage of a folded dipole is that the input impedance is increased by 4 times, and this was being fed by the twin cable which had a characteristic impedance of roughly 300 ohm. So, which provided a good impedance matching. So, log periodic antenna, as I said, it is being used for various techniques, for example EMI, EMC antenna, spread spectrum technique antenna, or even broadband antennas required for ground penetrating radar applications and so on. So, these are the different antennas we will cover. So, just to conclude, antenna technology is rapidly changing. In fact, the demand is increasing significantly. So, there is a requirement for innovative thinking to meet the challenges. In fact, there is a requirement coming every day increasing that people want broadband. Why we want broadband? Because of the requirement. If we have a broad bandwidth available, I can send multiple channels together, I can have a data transfer which is very, very fast. Then there are challenges about multi-band antenna. For example, a mobile phone requires several bands. So, we have CDMA or GSM 900, 1800, 3G, 4G, GPS antenna, Wi-Fi antenna, and the space required is very, very small. So, we really have to put all those multi-band antenna which should be compact as well as it should have a high efficiency, because if antenna is not efficient, then it will not radiate or receive the signal with the efficient manner. So, lot of losses will happen if efficiency is not good. Then people are demanding multipolarization. In fact, there are requirements that the same antenna should work as horizontally polarized antenna, vertically polarized antenna, circularly polarized antenna. So, switches are required to switch from one polarization to the another polarization. There is also a requirement for MIMO antenna, that stands for multiple input, multiple output. In fact, this is actually the new buzzword. So, a lot of research is going on in this particular area. This is basically to increase the channel capacity. As you know that the spectrum is becoming very expensive. We are going to have a spectrum auction in September 2016 in India, and government is planning to raise more than 5 lakh crore rupees. So, cellular operators have to shell a lot of money to buy the spectrum. So, in order to increase the capacity enhancement, multiple input, multiple outputs are required. Also, there is a demand for smart antennas. Now, again, smart antennas can have multiple things which are smarter than a normal passive antenna. So, many a times a simple passive, all the antennas are in general passive antenna, but we can make them smart by integrating maybe oscillator within the antenna or amplifier within the antenna, or build signal processing technique along with that, so that we can have adaptive antenna array and so on and so forth. Now, in all of these things, design is the most important thing. Now, this design really depends upon what is the application. For example, if we are designing the antenna for, let us say, satellite and defense application, their cost is relatively less important, but the performance is extremely important. However, if we are using it for commercial application, then the cost becomes very, very important. So, one has to design the antenna such a way that it can be mass produced at a very low cost. Now, antennas require precision manufacturing, okay, because when we are talking about microwaves or even millimeter waves, the dimensions are becoming very, very small. So, any little bit tolerance in manufacturing creates problem. So, we do require precision manufacturing, and that many a times leads to additional challenges also. So, generally what we do, so suppose if the bandwidth required is, let us say, for GSM 900, the bandwidth required is say 70 megahertz, 890 to 960. So, what I generally do, instead of designing for 70 megahertz, design for 100 megahertz. So, that way even if there are some manufacturing errors are there, it will still meet the requirement. And ultimately what we really want, everybody wants that antennas should be of low cost without sacrifice in performance. So, during this course of the lecture, I will emphasize wherever possible how the cost can be reduced without sacrificing the performance. So, thank you very much. We will see you next time. Bye.